So I have an integral here that we like to evaluate, the integral of e to the x cosine of x dx. And I'm going to do this using integration by parts. And if you watch the previous example, you probably have some idea of why. If you look at this integrand, excuse me, we have two expressions being multiplied together, and I can differentiate one of those and easily integrate the other one. When we have those two things going on, that makes me think integration by parts is going to be a good place to start. So to do that, I'm going to start by letting u equal e to the x and dv equal the cosine of x dx. Now, if you're wondering why I made that particular choice, hold on to that question. It's a good question. I'm going to come back to that again when we get to the very end here. So now this means du is equal to e to the x dx, differentiating both sides. And if I integrate both sides of the dv equation, we get v is equal to the sine of x. All right, so I've got our formula here, right? It's a formula for integration by parts. And using our particular u's and v's, this gives me the integral of e to the x cosine of x dx is equal to e to the x sine of x, that's uv, minus the integral of e to the x sine of x dx. That is the du part. Now, if you're looking at this, you could reasonably look at that and say, okay, why did he make that choice? If I didn't know off the top of my head what the integral of e to the x cosine of x was, there's no reason to believe I'm going to know what the integral of e to the x sine of x is, right? But this is where this one gets a little interesting. Right? Here's what I'm going to do. I'm going to do integration by parts a second time, right? I'm going to do it a second time on that right-hand integral. Now, I don't want to reuse u and v. Right? It's generally a bad idea to reuse your variables. But I really don't want to try, I don't know, w and z, because especially when students are just getting started with something, changing the variables in a formula like this can kind of get in people's heads. So what I'm going to do instead, I'm going to say, okay, I'm going to let u1 equal e to the x, and I'm going to let dv1 equal the sine of x dx. And now we'll do our integration by parts thing. du1 is equal to e to the x dx, and if we integrate both sides here, v1 is equal to negative cosine of x. All right, so we put those two things into our formula. I'm going to have the integral of e to the x cosine of x dx. I'm writing that over again for a reason. I'm going to want to see that over there on the left-hand side in just a minute. This is e to the x sine of x, looking at the right side, minus, be careful here because there's that minus sign floating around, minus e to the x cosine of x, minus the integral of e to the x negative cosine of x dx. All right, now the first thing I'm going to do is I'm going to straighten out all these negative signs. Right, so this is e to the x sine x. If I distribute this minus sign, this becomes plus e to the x cosine of x. And if I distribute it over here, now we've got three. We've got the one from the outside, we've got this one here, and this one here. So this is going to be minus the integral of e to the x cosine of x dx. Now let's write this in over here on the left side, because what I want you to notice, this is the neat little twist to this one. I've got e to the x cosine of x dx on both sides of the integral. So what I'm going to do is I'm going to add that to both sides. It's going to cancel the one on the right, and the left side is going to become 2 integral e to the x cosine of x dx equals e to the x sine x plus e to the x cosine of x. And this is the point where I'm going to go ahead and add my constant over here. Because now I have an integral equals a function that doesn't have an integral in it. And that's the point where I'm thinking, okay, this is where I need to add a constant. So now all I have to do to get my final answer is divide both sides by 2. The integral of e to the x cosine of x dx is equal to 1/2 e to the x sine of x plus e to the x cosine of x plus, okay, c divided by 2. That's also just a constant, but it is a different constant. So I'm going to go ahead and just put a different variable there. Put d instead. And that's it. Right? That's our final answer. All right, so we had kind of an interesting situation come up here where we had to use integration by parts twice. And in my head, this is like an official name or anything, but in my head, I think of this as a cyclic integral, right? Because this one of the parts, the cosine, its integral cycles around and eventually kind of comes back to itself, give or take a negative sign, right? And that's what let me do this slick little thing right here on line 3, where I just moved it over to the left side. That let me get to the final answer. All right, now at the beginning of this, I said, okay, wait until the end, and I'll explain my choice of u and dv. Again, if you remember, if you watched the last example, I talked about, if you're unsure, just work through all the cases, right? The other case you could have tried here was letting u equal the cosine of x and dv equal e to the x dx. Well, I encourage you to go ahead and try that case. Right? Go ahead and work through that one, because if you do, you'll see that you're going to get the same cyclic behavior, only this time it's going to be over on the u side instead of the v side, and in the end, you're going to end up with the same result. Right, so if you'd like to get the full context of integration by parts, you can click on the link here to see the corresponding lecture. And if you'd like to see another example, you can click on the link below. That's going to take you to a more complicated one, right? I'm kind of working our way up to bigger, more interesting problems. In that lecture, we're going to see how, in that example, we'll see how we can use integration by parts to derive what's called a reduction formula for evaluating the integral of a trigonometric function to a power. Right, and of course, if you like this example or found it helpful, please go ahead and click on the like button below.